G'day. This is another one of those bits and pieces videos that I do every so often. This one's on welding and some of the things I've learned over the years about welding. Now, I'm certainly not a qualified or professional welder, but these are some things that as I've been learning, I've picked up. Some of them have been explained to me by other welders, some of them I've just sort of worked out by myself, and so I thought I'd pass some of these on. If you're a proper qualified welder, by all means comment down the bottom if you disagree with something I've done, or if you think there's a better way of doing it. Always willing to learn, and that'll help everybody. But these are a few of the things that I've worked out about welding, and I'm hoping that there'll be people out there who'll sort of hear this and think, yeah, that's why that does that, or that's what I'm doing wrong, and that sort of thing. One of the secrets to successful welding that I've found is actually thinking about where the heat goes. And so, for example, if you want to put a weld in here, okay, when you put that heat in, or when you apply the weld, you're going to get heat going up here, you're going to get heat going out here, and you're going to get heat going out that way. Okay, so the amount of welding, the amount of current and all that sort of thing you need to put in there is going to be dependent on how fast the heat can get out of there, right? And that's really one of those secrets in welding that if you're self-taught you don't maybe pick up on until you're a way in. And I'm sure there are experienced welders out there who don't think about this consciously. If you say, can you weld this, they'll look at it and they'll work out how much current they need, and off they go. Okay. Now that's a T-joint. That's a you put a fillet weld in there. That's one thing. If you've got a lap joint of some sort like this, and you want to put a weld in there, the heat can only go here and here. So if you start thinking about that in terms of a constant amount of heat coming in compared to the T-joint, where there's a third way the heat can get out, you're going to need less heat here. And typically the rule of thumb I've been told about doing fillet welds versus doing flat welds like this is you probably want to bump your heat up by around about 10% or so, just to accommodate that. Having in the fillet weld case, having more metal for the heat to escape from. Now, of course, this is going to depend on whether you're using welding aluminium or stainless or steel or something else, because different materials have different heat characteristics. The heat characteristics, or the heat transfer that I've mentioned so far, have been assuming a steady state. Okay. If you then start looking at something like this, where you've got a piece of tube, you want to weld it onto another piece of tube, you've got the added complication of startup and finishing. Okay, so when you're starting here, everything's cold. The heat is really going to rocket out of there. Okay, once you're halfway along, you probably assume it's pretty much a steady state condition, that the heat is going out in the various directions in a relatively standard way. When you get to the end here, everything's heated up, and you then got the problem that you need to back your heat off because everything's already hot. There's nowhere else for the heat to go. It's going to build up and it's going to melt. And so when you see a weld where the front of it hasn't fused properly, it's because there's not enough heat there. When you see the end of a weld where onto some thin stuff like some tube, where it's actually melted away a piece of the tube, you're saying, well, there's too much heat there. Now, one of the nice things I like about TIG welding is that you can play with the heat on the run as you go. If you're doing stick or MIG, it's a little bit more complicated. And so typically if you're doing stick, I don't do MIG here, but typically if you're doing stick here and welding this up, you might actually strike your arc here and then go back a little bit until your weld puddle is established, and then move along. And when you get down to here, back off a little bit, just see how the metal is melting, it's flowing. But you may then come back a little bit just so that this has a chance to cool, and you're welding on existing weld which is a little bit thicker. Heat is all important in welding. You've either got too much or you haven't got enough. One thing, it's very gratifying to run a full-length seam along something, but if it's just to hold a part in place, it hasn't got any real force on it, you're probably better off just putting some stitches in. The reason being is that there's all this space that you don't then put heat into. The heat will spread throughout the part, and so the total heat you're putting in is less. It makes it a lot easier to control warpage and all that sort of thing. It's especially important in materials like aluminium, which conduct heat away really quickly and expand, and materials like stainless, which don't conduct heat away really quickly but still expand. And so, yeah, small tacks or small stitches for just holding things in place, much better than fully continuous seams. This is a lathe dog that I made up, and there's another video about that. But the interesting thing about this is that it's been welded along there, and you can see from the colours here how the heat has travelled up in a uniform fashion. And one thing you're looking for with your welding, or one thing that let's put it this way, one thing you don't want to see with welding is a very uneven heating pattern, because it probably means that somewhere something's been cold versus been a hot and that sort of thing. So you want a nice even colour if you can get it across there. But this just shows that the heat has travelled up, and the different colours correspond to different temperatures they've got to. That's basically an iron oxide there. A tip about tacking. I learnt this from some guys who were making large structures out of 3/4 inch plates, but what they do is they tack something together and then they grind their tacks back. Okay, so this one is maybe not too bad, but if you can see a couple of the other ones here, this is hot, that's a bit lumpy. So if I went straight at the top of that with my my TIG torch, I'd probably get a bit of a bump there. So if I grind that back so it's still holding the metal together, I'll probably find that I'll get a much smoother weld going over the top of that. So just something to bear in mind when you're tacking. Don't just think of the tack as being there and staying there. You can actually grind that back and get a neater weld over the top of it. I nearly got this wrong by getting it right, but at the last minute I managed to put my irons into the fire and get it wrong. What I was trying to show here was tacking. Now, for a start, when tacking, and these are just 2 bits of steel, I had them clamped to this bit of bar just to hold them flat. You want to get your arc in there, and you really want to hit it hard with the current. Now this is 1mm thick material, so I'd use around about 40 amps for the TIG torch on this, but I had it dialed up to 60 and I had the pedal flat down. What that does is that puts your heat in a very small area, concentrate it, you can get your filler in there quick, pull it away, and you've got a good chance of that solidifying. And that's actually not a bad tack. It's a little bit under flush, but for something going over the top, you're fine. This one here, same sort of thing applies, and you can see this pattern around here, by the way, is the heat. Now you can see that from the diameters there, I've got around about the same amount of heat into both of these. Okay, you can also see a slight discontinuity there where the 2 sheets join, so that's showing that the heat is, there's probably a little bit more heat on this side than there was on this side, and that's spread out. Where did I get it right by going wrong? What I was trying to show you was that if you don't have enough heat going in, so if this is 40 amps, and if I sort of only had the pedal halfway down and got 30 in there, I'd be heating this side up. The metal would be expanding, but it wouldn't be hot enough to actually get a bead going, right? Get a whirlpool going, okay? And so what'll happen is this material will buckle up, and then when you do get a bead going, you're going to get this discontinuity here, and you can see there's a slight step there, okay, and that can be a real pain. So when you're doing this sort of thing, you need to hit it with high current really quickly, not try and sneak up on it, just
bang into it. But the other thing that I was trying to show here is that if I'd managed to, if this was the first one I'd done, right, this whole piece would be ruined. And so what you want to do when you're doing this sort of stuff, clamp it down, tack it a number of places, and that way you've got a better chance of it not buckling, particularly buckling locally. Now, this one here, I actually did a false start just there, and that's contributed to the heat. But you can also see here, right, I've had my arc more on this side than this side, and you can see that by the heat affected zone there, or the oxide coloration. So that's a problem too. If I heat this side more than I heat this side, this one's going to buckle more than this one will. If I get the heat around about equal, it means they're both, fingers crossed, both going to expand, and it'll lessen my problems. In terms of welding, a couple of things to note. One is that I haven't got a sharp corner on this gusset. I've got a square corner, and I've been able to weld up to that square corner. If I'd had a sharp corner there, I probably would have got to that gusset and then it burnt back. Okay, so in terms of neatness, in terms of design for welding things like this, I would strongly recommend that you don't have sharp corners. You try and keep them square where you can, and then do your gusset thing. Another thing is here, I've got a bridging piece in here to strengthen things up, and the curved top is purely by accident. It was just happened to be the material I had, but I've got a stitch weld here. Okay, on the other side of this, I've got one of around about the same length. The reason for that is that if I have a continuous weld on one side, it's putting all this heat on this side, and so it's going to try and pull this gusset this way. So by putting one on the other side, I tend to centralize the forces. The other thing is that you don't really need welding everywhere. Okay, so that gap there, as well as having a little bit of clearance for the nuts, putting weld there is probably not going to help me too much in strength. So I've got the corners continually welded, and I've got a little bit in the middle, which is probably 40, maybe 50% of the width, and that's all I need. Okay, so that's a couple of, I guess, applied tips about design of weldments, of brackets, of reinforcings, of gussets, of all that sort of thing. Is firstly, you don't need to have weld absolutely everywhere, and secondly, you can get by, or you don't need to have sharp corners, and they'll cause you problems with your welding. So that's a few welding tips which might be of use to people. I'd also like to thank Graham and Adrian, a couple of welders I worked with at RFS, who did amazing things with TIG torches and were an inspiration to me to take up TIG welding. So please like, share, all that sort of thing, and we'll see you for the next one.